Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. So this is lecture number 49, and like we discussed in the previous class, right? It's been a while since we had a tutorial, so this is also going to be tutorial 11. Okay, so the last tutorial I think we had was roughly say some 9 or 10 lectures away, probably around lectures 38, 39, 40, something like that. Okay, yeah. So it's been some time, so we'll have a tutorial session. Probably this one, and the next lecture is also going to be another tutorial session. Okay, so how do we start it? What is the question for today's tutorial session? It is that the first question is, in this course, I've been talking about this particular phrase called as local thermal or local thermodynamic equilibrium often, right? I've been saying that without actually justifying it, right? And I've also been using expressions such as the Boltzmann distribution, the ratio of the number of molecules in any energy state, etc. What are they? Okay, so in this tutorial I'll be giving you a primer, not in great detail, but with sufficient detail that you understand it in the context of astrochemistry. Okay, all right. So what is local thermal equilibrium? So LTE stands for local thermal equilibrium, sometimes synonymous with local thermodynamic equilibrium also. Okay, right? Although there is a slight difference, but we're not concerned with that in this course. Okay, so what is local thermal equilibrium and how is it used to get the expression for the ratio of number of molecules in various energy levels, for the ratio of number of molecules in various energy levels. Okay, is it fine? Because we use some expression, right? For example, while deriving the Einstein coefficients, etc., we had to use what is called as the Boltzmann distribution, and that was all done under the LTE, that is like local thermal equilibrium conditions, correct? So we're going to be briefly elaborating upon what they are in this tutorial. So the answer is that. So now imagine you have a few molecules floating around. Okay, right? Let's say that we're dealing with the interstellar medium where the number density is around only 100. Okay, now when the number density is only 100 and we have molecules in any enclosed volume of space, right? Now these molecules move about in random directions. In fact, in the last lecture we saw that this facet led to the idea of Doppler broadening also. Okay, now so the molecules can move about in random directions. Will they all be having the same velocity as they move about? Well, the answer is obviously no, right? What about the kinetic energy therefore? Well, the mass of them are going to be same, right? The mass is the same, but the velocities are different. So therefore, the kinetic energies are also going to be different, correct? So mass is going to be the same. Kinetic energies, velocities are different, so kinetic energies are going to be different. Okay. Now, when the kinetic energy of each of the individual molecules is different, what about the temperature of each molecule, of each individual molecule? The temperature of each individual molecule is going to be different from that, right, of another molecule, etc. Correct? So when we say that the temperature is say some X Kelvin or Y Kelvin or something, It is not of the individual molecules. We're talking about the temperature for the whole macroscopic collection. That is, for all the 100 molecules put together, on an average, the temperature is so and so, right? And that is how we define temperature. Okay, right? So whenever any system can be associated with a unique value for a temperature, right? Such systems are said to be in local thermal equilibrium, right? So even though we have a collection of molecules, in the examples that we just saw, we may have a collection of molecules. The various individual molecules could be in possession of different temperatures. If we were to use the word temperature and take it down to individual molecules also, okay, because they have different kinetic energies. But on the whole, for the whole sample, if one average value, some kind of an average value can be attributed to the whole system, right, then that system is what is called as being in local thermal equilibrium. Now, this is a very important idea. Now, what do you think, just intuitively, let's say, I deal with a system that contains, like, say, 2 molecules, as opposed to, like a system containing 100 molecules, then a system containing 10 to the power 5 molecules, and a system containing 10 to the power 23 molecules. Now, I'll just write it down. So just, a small detour, a sub question you can say a system containing 2 molecules, and I have, like, let's say something containing 100 molecules, something containing 10 to the power 5 molecules, and something containing 10 to the power 21 molecules in the same volume of space. Okay, right? All within the same volume of space. Now, which of these systems do you think will be closer to LTE? So your expectation of LTE. Now, this is just a small sub question. What do you think? Well, if it's just 2 molecules, right? The molecules behave randomly. So therefore, the direction in which, like, one molecule is traveling, the direction in which the other molecule travels, they need not be correlated, right? The velocities need not be correlated, independently moving of each other. And so therefore, it may not be that easy to come up with any average value of a temperature, okay, right? So when the number density is extremely low, that is, when you have, like, very few molecules, such as 2 molecules, 3 molecules, etc., our expectation is that the system will not be under LTE. Okay, right? So likewise, with 100 molecules also, our expectation is that, LTE is perhaps not so valid. But the minute, you have, like, a larger number, that is, like, 10 to the power 5, which is the number we're talking about in dense molecular clouds, or like the dense cores of circumstellar envelopes, right? Or, the number density which is closer to Earth, right? We can assume that, yeah, because there are enough molecules, they can all move about in various directions, right? They can all move about in various directions with different values of kinetic energies. The overall temperature can be averaged out. The overall temperature can be averaged out as a single value. So therefore, it's a fair enough assumption that the system is in local thermal equilibrium. So the number density plays a very important role in deciding whether a system is in local thermal equilibrium or not. Okay. So this local thermal equilibrium is extremely important for us to predict, various properties, such as, like, the number of molecules in various excited state versus ground state, etc., etc. Okay. The idea is that, in fact, in the whole field of astrochemistry, astrophysics, and astronomy, okay, right, LT is a very powerful approximation. The Boltzmann distribution, about which we are going to see soon now, right? Yeah, that is the next idea. That is just one particular aspect of LT. You can have mechanical equilibrium also, that is when 2 systems have the same pressure. And you can have other types of equilibrium, overall thermodynamic equilibria, under which conditions various equations can be developed, and using them we can compute the properties of space, such as, for example, the radius, the diameter, etc., etc. Okay, are we good? But why this LTE condition is extremely important? Because it is the LTE conditions which help us, come up with like various equations to compute the properties of the entities that are there in space. Okay, right? And when is LTE going to be holding good? Preferably under, or preferably under the case where the number densities are large, because then the overall kinetic energy of the system can be averaged out, with the fluctuations being much lesser. Okay, that's it. So this is a qualitative understanding of what LTE means. Now what we're going to do is, we are going to, so the first part of the question, that is what is LTE. Now we're going to be talking about how this LTE is used to get the ratio of the number of molecules in various energy levels. Okay. Now, as you might have already guessed, this aspect, the expression for the ratio of the number of molecules in various energy levels, it is based on what is called as the Boltzmann distribution. So this Boltzmann distribution is obtained from LTE approximations, where you can uniquely define a temperature for a collection of the more technical phrases, an ensemble, ENSEMBLE, okay, right? An ensemble of various molecules, okay, right? So now what is the Boltzmann distribution and what is the starting point? Okay, now you consider some system, okay, right? Consider a system such that its energy levels are E0, E1, E2, blah blah blah, right? Okay, right? I don't care about the upper limit. What is an example of such a system? Why should a system have multiple energy levels? Well, take for example, the simplest hydrogen atom, right? If you consider the hydrogen atom, it has different energy states, right? The energy depends on 1 over n square, right? If you talk about the interaction energy of the electron with the nucleus, right? The energy depends on 1 over n square. This you've already learned in your high school as part of the Bohr's theory, as well as from quantum mechanics, correct? As far as to quantum mechanics, you understand that E is proportional to 1 over n square, right? So there are different energy states corresponding to n equal to 1, which is what we call as E0. Always the lowest energy state is denoted by E0 and not E1, okay, right? So we have the different energy states such as E0, E1, E2, blah, blah, blah. For example, if you consider the hydrogen atom, it could be n equals 1, n equals 2, n equals 3, etc., etc. Okay, right? So we have a system with various energy levels, okay? And in each of these energy levels, E0, E1, E2, etc., let's say there are N0 molecules. N0 molecules present in the state E0, N1 in the state E1, N2 in the state E2, etc., etc. Now, again, let's say if you take 1 mole of hydrogen atom, right? What is 1 mole? 1 mole corresponds to a very large number, say approximately 10 to the power 23 or something like that, right? Now, out of all these 10 to the power 23 atoms, right? Not all of them need to be lying always in the lowest energy state, right? Of course, you would expect that predominantly molecules would be lying in states which are lowest in energy. But however, there is always going to be some kinetic energy for some of the atoms that at any instant, some of the higher states may also be populated, right? So therefore, let's say, let's say from out of the 10 to the power 23, a fraction of them is occupying the energy state E0. And likewise, some more molecules are occupying the state E1, E2, etc., etc. Are we clear? So these two statements, right? These two statements give us two mathematical conditions such that the summation of all the molecules, okay, right? The summation of all the molecules, right, present in various states, where I equals 0 to some upper bound, okay, right? To some upper bound, right? So that is going to be the total number of molecules, which is denoted by this capital N, all right? Similarly, the total energy of the system, okay, right? the total energy of the system, which I'm denoting by E, right? That is given by, once again, summing over, right, the energy of all the molecules present in all the states, starting from some lower bound, which is I equals 0, to some arbitrary upper bound, right? Such that the total energy of the system and the total number of molecules, right, which are fixed. So note that N and E are constant. Okay, right? So for this system, the total number of molecules, right, and the total energy is constant. In other words, you're not going to add more molecules from the surroundings, okay, right? Or going to be, talking about any exchange of energy, okay, right? So the two conditions are the sigma or I, Ni is equal to capital N, which is the total number of molecules is a constant, and the energy of all the molecules present in all the states also adds up to the total energy of the system. Okay, so these are the two conditions on the system. Okay, now next, I'll call this page number 4. We are going to be defining a new term. Okay, right? We'll be defining a new term called weight W. Weight, okay, right? Denoted by the symbol W for the system. Now, this thing weight, okay, right? This weight of a system, right, is, somewhat, I'll give you a working definition, okay? It's understood to be the number of ways via which any particular combination of Ni and Ei, Ni's and Ei's is reached. For example, you go back to the system we are considering. Now, let's say that N0 molecules are in the state E0, N1 in E1, N2 in E2, etc., etc. At any instant, right? At any instant, some molecules could be in E0 and some in E1. The point is, let's say, with time, right? With time, this number keeps changing, right? With time, this number keeps changing. Because the molecules possess kinetic energy, the molecules possess kinetic energy, the number of molecules present in E0 at any instant need not be, at any instant t, need not be the same as it is at some other instant t plus dt, right? So therefore, even though like at all instants, this equality, that is like sigma over I equals 0, Nii is going to give you the total energy, and that the total number of molecules is also going to be the constant. At any level, right? At any level, there is always going to be a flux between the various energy states. Okay, right? Now, this therefore, right, leads to the idea of what is called as a weight, which tells you, what are the various number of ways in which any particular combination of Ni's and Ei's is reached. Okay, it is given by the mathematical formula using, very simple combinatorics. This can be derived to be n factorial, capital N factorial, divided by n0 factorial times n1 factorial, n2 factorial, etc., etc. And it goes subject to how many energy levels are here. Okay, right? So that is how you define the weight of a system. And what does it roughly give you physically? It tells you, the number of ways via which any particular combination of E0 and Ei and Ni can be reached. Noting that your E0 and the Ei's and Ni always keep changing with time because of the simple idea that the molecules possess kinetic energy. All right. So I'm just going to save this expression. I'm going to call this expression W. Okay, right? And from expression W, I'll delete this part. See, so we shall be mathematically manipulating this expression W a lot in this course. Okay, at least in the next few lectures. So let's take the ln of this particular expression, ln W. Okay, ln W. That's going to be something useful for this. So your ln W can be, written as ln n factorial, right? Minus, it's right, it's a by b form, so I can always write it as sigma over I ln small ni factorial. Are we good, right? So you understood what we did, right? So we're going to take the logarithms on both sides, but ln of a by b is going to be ln a minus ln b, but there's a product here. So therefore what I've written is, I've just used the summation over here. Okay, right? We get this. Now, so we have this expression, such that ln w is ln n factorial minus sigma over I ln small ni factorial. Now, we're going to make an approximation here, and we're going to use ln of x factorial is x ln x minus x. This is what is called as the Stirling's approximation. And I'll in fact give it to you as a homework, right? Take it as a homework and keep varying the various magnitudes of x here, right? And figure out if you can match LHS and RHS. Okay, that will be a homework for you. Now, using this approximation, your ln w is going to be becoming n ln n minus, right? So this is what applying the Stirling approximation to this term, you get this, and this is going to be becoming my sigma over I ni ln ni minus ni, right? So this is a bracket and this is a sigma. Okay, right? Basically, whatever is inside the sigma, I have replaced it with this with the RHS of the approximation. Okay, right? So, but notice that your sigma over I ni is equal to capital N, right? That is what we started with. Okay, so using that, this expression overall becomes ln w is equal to n ln n minus sigma over I. I'll write the sigma properly. Ni ln ni. Okay, right? Let's just call this, this expression we'll be using subsequently. Okay, so let us call this expression to be the expression for ln w. So I'm just going to call this expression LW. Okay, so why did we get this ln w? I've not told you yet. Okay, so I just had an expression for w, and I told you that we shall be using ln w in some place, right? And so using an approximation, I got ln w, and I used an approximation to get this formula given in the equation LW. Just note this. Okay, next note that now we were discussing about the weights, right? This W, which is the weight, which tells us about the various number of ways in which any particular combination of NIs and EIs could be reached, right? Now, for the system to be more stable, right? For our system to be most stable, we want to maximize, okay, please recall, I'll write a statement and I'll explain it. We want to maximize the number of ways different EIs and NIs could be reached. Why is this? What am I talking about? Well, in general, right? In general, any system, containing very many molecules, right? The example of hydrogen atom that I gave you, right? Containing very many molecules will want to be, will instantaneously change, right? Its values of N0 and E0 at each instant. Okay. As it changes, the most stable system is something, which has accessed all these possible values of E0s and N0s. Okay, so I'm not using any technical jargon. Technically, this is called as maximizing the entropy. Okay, right? But I've never used the word entropy before in this course, so I'm not even taking the phrase entropy. But instead, our task should be that we should maximize the number of ways such that all possible E naught N naught combinations are accessible to the system. And that way, we shall be getting a system that is more stable. Okay, right? So we want to maximize the number of different ways in which the EIs and NIs could be reached. In other words, what is our task? We need to maximize the weight W, right? The weight W that we defined for this purpose. Okay, but due to mathematical convenience, when we say I have to maximize W, as it will be turning out, right? Maximizing W is the same as maximizing ln W. So maximizing W is the same as maximizing ln W. Okay, right? This can be mathematically shown. If you want to assuming that the ln of a function could be defined, right? If you maximize this, it's the equivalent as maximizing this also. Okay, right? And because of the ease of mathematical operations, we choose to maximize ln W in particular. Okay, it is not just maximizing ln W, but it is maximizing ln W subject to the conditions, right? Subject to the conditions that your total number of molecules is given by the sum of molecules in each of the energy states, and the total energy, which is also a constant, just like the total number of molecules, is given by the sum of the product of each molecule in each energy state. All right. So what we need to do next is, in order for us to arrive at what is called as the Boltzmann distribution, we need to maximize ln W. We need to maximize ln W subject to the conditions that the total number of molecules is fixed and the total energy is given as the sum of products of the molecules in each energy states times the energy of each of the states. All right. So this is something we shall continue with in the next tutorial. Thank you so much.